The size of a transformer is determined by the power it must handle. The power rating of a transformer is expressed in volt amperes, kilovolt amperes, or megavolt amperes. The general formula for transformer sizing is transformer volt ampere rating equals load volt ampere times load factor times safety factor, where load volt ampere is the apparent power of the load in volt amperes. Load factor is a factor that adjusts for the varying load over time. Typically, a load factor of 1.25 or 125% is used for industrial loads. Safety factor is a factor that provides a margin of safety to prevent transformer overload. Typically, a safety factor of 1.1 or 11% is used. For a specific case, load volt amperes equals 250 amps times 575 volts, which equals 143.75 kilovolt amperes. The load factor equals 1.25. The safety factor equals 1.1. Therefore, the transformer volt ampere rating equals 143.75 kilovolt amperes times 1.25 times 1.1, which equals 202.5 kilovolt amperes. Based on the calculated volt ampere rating, the next available standard transformer size would be a 250 kilovolt ampere transformer. The delta and Y configurations of the transformer windings affect the voltage and current relationships. With the delta configuration, the secondary windings are connected in a closed loop or triangle. This results in a 57.7% voltage drop and a 73.2% current increase. With the Y configuration, the secondary windings are connected in a star shape. This results in a 33.3% voltage drop and a 57.7% current increase. In the case of a step-up transformer, the primary voltage of 480 volts is lower than the secondary voltage of 575 volts. Therefore, a delta Y transformer would be appropriate. Using a delta Y transformer with a 125% load factor, the primary current equals 250 amps times 575 volts divided by 480 volts times 1.25, which equals 367.7 amps. The transformer selected at 300 kilovolt amperes is slightly larger than the calculated size of 250 kilovolt amperes. This is acceptable and provides a bit of extra capacity. When sizing a three-phase transformer, there are several key considerations to ensure it meets the demands of the load while operating safely and efficiently. Firstly, calculate the total kilovolt amperes required by the load. This involves summing up the volt amperes for all connected devices or equipment, taking into account their individual power factors. For motors, it's crucial to use the nameplate horsepower rating and convert it to kilovolt amperes, remembering to account for the motor's efficiency and power factor. Secondly, apply appropriate demand factors to the load kilovolt amperes. Demand factors account for the fact that not all loads operate at their maximum rated power simultaneously. These factors are typically determined based on historical data or industry standards for similar types of loads. Using demand factors helps prevent oversizing the transformer, which can lead to inefficiencies and increased costs. Thirdly, consider future load growth when sizing the transformer. It's advisable to add a safety margin of 20 to 25% to the calculated load kilovolt amperes to accommodate potential increases in demand over time. This ensures that the transformer will be able to handle future loads without being overloaded. Fourthly, select a transformer with a kilovolt ampere rating that is equal to or slightly larger than the calculated load kilovolt amperes, including the safety margin. Standard transformer sizes are available in specific increments, so it's often necessary to choose the next larger standard size. Fifthly, determine the appropriate voltage ratings for the primary and secondary windings of the transformer. The primary voltage should match the available supply voltage, while the secondary voltage should match the voltage requirements of the load. It's essential to consider voltage drop in the distribution system when selecting the secondary voltage. Sixthly, consider the transformer's impedance, which affects voltage regulation and fault current levels. Lower impedance transformers typically provide better voltage regulation, but result in higher fault currents. The impedance should be selected to balance these factors based on the specific application requirements. Seventhly, evaluate the transformer's cooling method. Transformers are typically cooled by either natural air convection, forced air cooling, or liquid immersion. The cooling method should be chosen based on the transformer's kilovolt-ampere rating, ambient temperature, and installation environment. Eighthly, consider the transformer's efficiency. Higher efficiency transformers reduce energy losses and operating costs. Efficiency is typically expressed as a percentage and varies depending on the transformer's load level. Ninthly, ensure that the transformer complies with relevant industry standards and regulations, such as those set by the National Electrical Manufacturers Association and the Institute of Electrical and Electronics Engineers. These standards specify requirements for transformer design, testing, and performance. Tenthly, consult with a qualified electrical engineer or transformer manufacturer to ensure that the selected transformer is suitable for the specific application requirements. They can provide guidance on transformer sizing, selection, and installation, taking into account all relevant factors. When dealing with delta and Y configurations in three-phase transformers, understanding their impact on voltage and current relationships is crucial for proper application and system design. Firstly, in a delta-connected system, the line voltage is equal to the phase voltage, while the line current is equal to the square root of 3 times the phase current. This means that the voltage between any two lines is the same as the voltage across each individual winding, but the current flowing in each line is higher than the current flowing through each winding. Secondly, in a Y-connected system, the line voltage is equal to the square root of 3 times the phase voltage, while the line current is equal to the phase current. This means that the voltage between any two lines is higher than the voltage across each individual winding, but the current flowing in each line is the same as the current flowing through each winding. Thirdly, the choice between delta and Y connections depends on the specific application requirements. Delta connections are often used when a stable voltage is required, as they provide a closed-loop path for circulating currents, which helps to minimize voltage imbalances. Y connections are often used when a neutral point is required, as they provide a convenient point for grounding and for supplying single-phase loads. Fourthly, when stepping up or stepping down voltage, transformers are often configured with a delta connection on one side and a Y connection on the other side. This allows for both voltage transformation and the provision of a neutral point. For example, a delta Y transformer can be used to step down voltage from a high voltage transmission line to a lower voltage distribution system, while also providing a neutral point for grounding. Fifthly, it's important to consider the impedance of the transformer when selecting delta or Y connections. The impedance affects the fault current levels and the voltage regulation of the system. Lower impedance transformers typically provide better voltage regulation, but result in higher fault currents. Sixthly, when connecting transformers in parallel, it's important to ensure that they have the same voltage ratio, impedance, and phase angle. Otherwise, circulating currents could flow between the transformers, leading to overheating and reduced efficiency. Seventhly, the delta and Y connections can also affect the harmonic content of the system. Delta connections can trap certain harmonics, while Y connections can allow them to propagate. Therefore, it's important to consider the potential for harmonic distortion when selecting delta or Y connections. Eighthly, when working with delta or Y connections, it's important to use proper grounding techniques to ensure safety and to minimize the risk of electrical shock. Grounding can be achieved by connecting the neutral point of a Y-connected system to ground, or by using a grounding transformer in a delta-connected system. Ninthly, it's important to follow all applicable electrical codes and standards when installing and maintaining delta and Y-connected transformers. These codes and standards provide guidance on proper wiring practices, grounding techniques, and safety procedures. Tenthly, it's always advisable to consult with a qualified electrical engineer when designing or modifying a three-phase power system with delta or Y-connect transformers. They can provide expert advice on transformer selection, connection methods, and system protection. When sizing a transformer, it's crucial to consider several factors beyond just the initial load requirements. These factors ensure the transformer operates efficiently, reliably, and safely over its lifespan. Firstly, determine the accurate load demand. This involves not only summing up the connected loads but also applying demand factors that reflect the actual usage patterns. Demand factors account for the fact that not all loads operate at their maximum capacity simultaneously. Utilizing historical data or consulting industry standards can help determine appropriate demand factors for different types of loads. Secondly, account for future load growth. Electrical systems often evolve, with new equipment added or existing loads increased. Planning for future expansion prevents overloading the transformer and ensures it can accommodate increased demand without requiring a costly replacement. A typical allowance for future growth is 20 to 25%, but this can vary depending on the specific application and anticipated changes. Thirdly, consider the transformer's operating environment. Ambient temperature, altitude, and ventilation can all impact a transformer's ability to dissipate heat. High ambient temperatures or poor ventilation can reduce the transformer's capacity, requiring a larger unit to compensate. Dating factors provided by the manufacturer should be applied based on the specific environmental conditions. Fourthly, evaluate the impact of harmonic loads. Nonlinear loads such as variable frequency drives and electronic equipment generate harmonic currents that can overheat the transformer and reduce its lifespan. If harmonic loads are present, a K-rated transformer should be selected. K-rated transformers are designed to withstand the additional heating effects of harmonic currents. Fifthly, analyze the transformer's loading profile. The loading profile describes how the load varies over time. If the load is highly variable, with frequent peaks and valleys, a transformer with a high kilovolt ampere rating may be necessary to prevent overheating during peak demand periods. Sixthly, consider the transformer's efficiency. Transformers are not perfectly efficient, and they lose some energy in the form of heat. Higher efficiency transformers reduce energy losses and operating costs. Energy-efficient transformers typically have higher initial costs, but they can save money over the long term through reduced energy consumption. Seventhly, determine the appropriate voltage regulation. Voltage regulation is the change in secondary voltage from no load to full load conditions. Poor voltage regulation can cause equipment to malfunction or operate inefficiently. Transformers with lower impedance typically provide better voltage regulation. Eighthly, consider the available fault current. Fault current is the current that flows during a short circuit. The transformer must be able to withstand the available fault current without being damaged. The available fault current can be calculated using the transformer's impedance and the source impedance. Ninthly, select a transformer that meets applicable industry standards. Industry standards, such as those set by the National Electrical Manufacturers Association and the Institute of Electrical and Electronics Engineers, specify requirements for transformer design, testing, and performance. Compliance with these standards ensures that the transformer is safe and reliable. Tenthly, consult with a qualified electrical engineer. An electrical engineer can help assess the specific requirements of the application and select a transformer that is properly sized and configured. They can also provide guidance on installation, operation, and maintenance. Understanding the impact of delta and Y configurations is crucial when working with three-phase transformers. These configurations affect voltage and current relationships, grounding methods, and harmonic distortion. Firstly, voltage and current relationships differ between delta and Y connections. In a delta connection, the line voltage equals the phase voltage, while the line current is the square root of 3 times the phase current. In a Y connection, the line voltage is the square root of 3 times the phase voltage, while the line current equals the phase current. Secondly, grounding methods vary depending on the connection type. Y connections allow for a direct neutral connection, providing a path for ground fault current. Delta connections typically require a grounding transformer to establish a neutral point. Thirdly, harmonic distortion is affected by the transformer connection. Delta connections can trap certain harmonic currents while Y connections allow them to flow. The choice of connection can impact the overall harmonic content of the system. Fourthly, impedance considerations are important for both delta and Y connections. The transformer's impedance affects voltage regulation and fault current levels. Lower impedance transformers provide better voltage regulation, but result in higher fault currents. Fifthly, parallel operation requires careful consideration of transformer characteristics. Transformers connected in parallel must have the same voltage ratio, impedance, and phase angle to avoid circulating currents. Sixthly, voltage transformation can be achieved using different delta and Y combinations. Delta-Y transformers are commonly used for step-down applications, while Y-delta transformers are used for step-up applications. Seventhly, unbalanced loads can create challenges for both delta and Y systems. Y systems are generally better suited for handling unbalanced loads, as they provide a neutral connection to mitigate voltage imbalances. Eighthly, fault current calculations are essential for protecting transformer systems. The transformer's impedance and connection type influence the magnitude of fault currents. Ninthly, overcurrent protection devices, such as fuses and circuit breakers, must be properly sized to protect the transformer from overloads and short circuits. The selection of these devices depends on the transformer's kilovolt-ampere rating, voltage, and connection type. Tenthly, regular maintenance is crucial for ensuring the long-term reliability of transformer systems. Maintenance activities include inspecting connections, testing insulation, and monitoring oil levels. When sizing a transformer, it is essential to apply sound engineering practices and consider all relevant factors. This ensures that the transformer operates efficiently, reliably, and safely, providing a stable power supply for the connected loads.